Welcome to Mickey Study Circle channel. In this video, we shall see how to perform the stress analysis of a trusses, mainly a rail bridge, using the Ansys Workbench software. Moving on to the problem statement, we have a small railroad bridge which is constructed of steel members, all of which have a circular cross-sectional area with its diameter being 0.25 meters. A train stops on the bridge and the loads applied to the truss on one side of the bridge are as shown in the figure. Determine the nodal deflections, reaction forces, and stress for the truss system. Consider the Young's modulus to be 200 GPa and the Poisson's ratio of zero point 0.3. So, as you can see here in the figure which is given, it is composed of totally 7 nodes, and we can just model this using the triangular structures as shown here. So each section is having a length of 3.5 meters, and also the total height of the section is 3 meters. And also you can just see that the angle of 60 degrees is given here. So there are totally 4 loads which is acting, that is at node 1, 3, 5 and 7. Coming to the supports, it is having a fixed support at the node 1, and there is a roller support which is provided at the node 7. So all the degrees of freedom is to be constrained at the node 1, and at node 7 it is the deflection which is possible only along the x direction, but in the y direction the deflection is 0. So with this data, let us see how to perform the stress analysis and determine the parameters of the nodal deflections or the displacements, followed by the reaction forces and the stress within this truss system, which is a railroad bridge. So these are the parameters to be determined. So first we need to compute the values of the reaction forces, followed by the nodal stresses and the total deformation of the member. So double click on this and you get to see this. So you can just rename this into truss analysis. Now let us feed the material data. So let us use the engineering data component. Enter material 1. So for this material, select isotropic elasticity and feed the values of the Young's modulus, which is 200 GPa as given in the problem statement. So change the units from pascals to gigapascals. Also feed the value of the Young's modulus as 200 GPa followed by the Poisson's ratio, which is zero point 0.3. So now for this material, I have defined the values of the Young's modulus and the Poisson's ratio. So now let me close the engineering data, go for geometry, right click and select the design modular geometry, in which I'm going to design the physical continuum. So let me select the XY plane and make it normal to the screen and ensure the units is in meters. Let me switch over to the sketching mode, select the line option and draw the rough sketch of the physical continuum given in the problem statement. So these are the 3 lines of the base of the rail bridge, followed by the triangular structures connecting the endpoints of all the lines. So ensure you start from the point P and you terminate at the point P. So now let me connect all the peaks by a line. So just make a rough sketch and later on we can apply the constraints. So now let me go to the constraints and then select horizontal constraint first and make these 2 lines horizontal. Go for equal length and select these 3 lines and make them equal. Let us select the parallel condition and all the opposite edges, make them parallel. Similarly on the so select this line and make them parallel. Similarly this edge and this edge, make them parallel. So now we'll go for the dimensions. Select the angle first. So select this line and this line. So it is showing the angle. So you can just see this. So this is the exterior angle which is being shown here. So the angle here was 60. So in order to be a complete angle, it has to be 360. So it has to be 300. So let me change the value to 300. Now let me go for the general and select the end-to-end distance. So this is L2, and L2 as given in the problem statement, it is 3.5 each. So into 3 is 10.5 meters. So we can use this option to zoom to fit. And next, go for the vertical distance. Select the peak and this line, and you can just see that it is vertical. So change it to say 3 meters. And the truss structure is ready as given in the problem statement. So now we can go for the concept and select lines from sketches. So we have created the sketch using the lines. So now select the sketch one, click apply, and then click generate. So you can just see that one part, one body is created, and we need to assign the cross section for this particular lines. So for that, go for concept, select cross section, select circular. So the diameter is 0.25 meters. So that is the diameter which is given in the problem statement. So we can assign the radii. So we can assign the radii for the circular component as 0.25 divided by 2, which is equal to 0.125. So 0.125 meters. So you can just see that the area is calculated automatically. So 0.125 meters is the area of that is the radii for each member. So now let me select the line body and select circle 1 as the cross section, and then click generate. Now we can go for the view option and select the cross section solids. So now you can just see that the truss member is applied with the required circular cross section. So with this, we complete the creation of the 2D model of the truss member. So we'll close this design modeler and move on to the analysis part. So we'll just double click on the model. So it will directly import the geometry created in the design modeler for the analysis. So in this step, we are going to apply the material, apply the boundary conditions, apply the loads and the supports, and then we are going to compute the values of the displacements, reaction forces, and also the stress distribution within the rail bridge. So now you can just see that the component is imported. You can just go for cross section so that you get to see the entire solid object as given in the problem statement. So now click geometry in this project tree, select the line body, and by default the assignment is structural steel. Change it to the material that you have defined. So now it has been applied. So I can just keep it as the line structure so that the application of the boundary conditions is pretty easy with this structure. So let me go for mesh and select generate mesh. So you can just see that this is the discretized object now. So now I can just go for the views and keep the view as front view so that the application of the loads will become easy. So we'll take the loads as given in the problem statement. So in the problem statement, we have got at node 1 a load of 280 kilonewtons which is acting. So let us apply that load first. So go for static structural, and you can get to see that there is something called as environment. So select this environment and select the force and select define by components, and it is acting in the y direction, so it is minus of 280 kilonewtons. So we can just change the load to 280 followed by 30 newtons, and it is asking where to apply. So for that, select the vertex and select this vertex and click apply. So the load is acting here. Similarly, the second load is at this point, which is having a magnitude of 210 kilonewtons. So again, ensure you are in the vertex mode. Go for the force again, change the vector to component and select the y component. It is minus 210 kilonewtons, and select this particular vertex. Click apply. Again, let us apply the load. So go for force and select this particular component. Change define by component, and the magnitude is again 280 kilonewtons. So 280 followed by three zeros. Click apply. So the load is applied here. So force is this, force 2 is here, force 3 is here. So we'll end up by adding the next force, which is at the last node. So it is at 360 kilonewtons of magnitude. So let me go for force again, and then select this vertex of the truss structure, change it to components. The y component minus of 360 followed by 30 newtons, that is 360 kilonewtons. So now it is applied here. So all the four forces are applied. Let us apply the boundary conditions now. So go for fix it and select this particular node, click apply. So this particular node is fixed now, but here I need to apply a roller support. So for that I've got something called as displacement. So select displacement, and here let me just assign the value of the y component as 0 and select this particular node and tell apply. So you can just see that the y direction is constrained, and it is free to move in both the x and the z directions. So now I've applied the forces and the required constraints, that is the fixed support and the displacement. So select solution and right click and select solve. So the mathematical model is being solved here. So maybe the student edition will not allow us to give the loads of this high magnitude. So what we can do is we'll just change the load to just say 280 newtons, and select force to change this to say minus of 210 kilonewtons. So force minus 280, and force 2 is minus 210. Force 3 is minus 280 newtons. Force 4 is minus of 360 newtons. So now you can just go here and select solve. So now the results are ready. So maybe the loads were of too high magnitude for the student edition. So now go for solution and select insert. Select the beam tool and add the beam tool here, and right click on the beam tool and click evaluate all results. So in the beam tool, if I click on direct stress, I'll be getting the magnitude of the stress within the member. So I can just go for the display and select cross sections, thick shells and beams. So you can just see the actual 3D representation of the truss member and the distribution of the stress within the member. So if I need to select the particular node or any element and probe the value there, you can just select the probe and click it here, so that you get the values of the direct stress at that particular node. So next thing is I need to determine the deflection. So go for uh, solution and select total deformation, and right click until retrieve this result. So this is the total deformation in the member. So 5.07 E5 is the maximum value of the deflection. Okay, so you can just record the values. So this is the results, So this is the deformation. Coming to the stress, this is the stress distribution. You get to see the tabular data here and also in the legend that is given here. So now let us compute the reaction forces. So right click on solution, select insert, select probe and select force reaction. So it is asking where, so select at the fixed support and right click until retrieve this results. So you get the force reaction. So the magnitude of the load in x, y, and the z directions is given, and the total, that is the result component of the load, is 514.23 newtons at the support. So let me go for the next component, that is where the displacement is applied. Right click until retrieve this results. So you get to see the resultant or the reaction force here, where only the y direction was constrained and x and z components were there. So you get the load here in the y direction alone, that is 615.77 newtons. So this is the magnitude of the reaction force at the supports. So now let us see how to capture the image. So this is with respect to the total deformation. So I can just go for the display here, and then or go for the result, select images, select image to clipboard, go for the file where you need to put your results. So let me select this PowerPoint presentation. I'll select a new slide and I'll enter deformation, and just right click and paste. So I'm getting the deformation figure here from the workbench directly. Similarly, let me repeat the step for stress. So let me delete this, get back to the workbench file, select the direct stress, go for images, select image to clipboard. So paste it here. You get the image of the stress distribution in the member. Right click, select a duplicate slide, and you can just go for the reaction forces, and then select the force reaction here. Go for images, image to clipboard. So you get the reaction forces. So you can just export this table also as the text file. So I'll just save this as reaction force on the desktop. Click save. So now we can just go see how to extract. See here in the Excel sheet we have got the reaction forces. So the reaction force in newtons in the x direction, y direction, and also in the y direction. So this is the total reaction force. So this is how I can extract the tabular results from the Ansys workbench. So with this, we complete the video tutorial of the stress analysis of the truss member using the Ansys workbench. So wherein we have determined the values of the total deformation, the stress distribution within the member, and also the reaction force components. So you can just take the reaction force both at the support as well as the fixed support and as well as the displacement. So this is the component. So if you want to get the front view, just go for display, select views and select front, and you get this view. So you can just go for right click, image to clipboard. Even this will also work out. Go for the PowerPoint presentation, duplicate the slide, remove the previous image and paste this. So you get the reaction force which is shown here. So we have computed the values of the deformation, stress, and also the reaction forces within the member as the parameters to be determined in the problem statement. Thank you all for watching.